We will continue our topics. This is topic one, chapter one, introduction to fluid mechanics, and we will discuss the topic of dimensions and units. We will start with this a piece of news here. This is from 1999. So NASA lost 125 million USD Mars climate orbiter because their engineers did not convert a measurement from English to metric because so when they were building this climate orbiter, they have different engineers from different teams, right? And then uh, one team from the Jet Propulsion Lab used the metric system, and Lockheed Martin in Denver, another team in that project, design and build spacecraft using English system. So they did not write the units properly, and then they have they lost this Mars probe. Okay, and this is a very basic uh, very basic concept that every engineer should know, that you need to use the same unit. Okay, even NASA sometimes, I guess, because I don't know what happened, but the engineers took this for granted and they did this extremely poor decision to not properly check their units, measurement units. Okay, so the simple error called brought losses to NASA to this huge amount, 125 million USD. Okay, so this brings us to the importance of understanding uh, about units, dimensions, and units. Okay, so a dimension is a measure of any physical quantity without assigning numerical value. So it serves as a qualitative description to identify the nature or type of characteristics such as length, mass, or time. Okay, so when you talk about dimension, you do not talk about any value that is assigned to it. It's just a description. Okay, this is very, I think it's quite self-explanatory. So you have length, mass, or time, and also you have temperature. While unit is an arbitrary name. Well, it's not random, but it's a chosen name by someone. And magnitudes that is assigned to dimensions to allow for quantitative comparison. So, for example, if the dimension is length, a standard unit would be uh, a meter, 1 meter, or one foot, or a foot. That is a unit. Okay, so this is the difference between dimension and unit. So this is the primary dimensions that we deal with in fluid mechanics. So we have mass, length, time, and temperature. Okay, so we have mass, length, time, and temperature. And the symbol that we use for mass is this capital M. Length we use L, capital L. Time we use capital T, and temperature we use I don't know what this symbol is. Maybe capital theta. Okay. Uh, we have two types of dimensions, the primary dimension and also the secondary dimension. The primary dimension is a small group of fundamental dimensions from which all others can be formed. And the common system, which is important for our case, is includes length, time, mass, and temperature. So these are the primary dimensions. You cannot create this dimensions from any other dimension. So these are the basics, the most basic form of dimension, the primary dimensions. And then you have secondary dimensions, which are the quantities whose dimensions are expressed in terms of the primary quantities, such as area. For example, area. Area, the unit for area in the uh, SI system is meter square. So again, we have the primary dimension, length, mass, time, and temperature. Okay, length, mass, time, and temperature. So let's say we have area. Okay, for us, the most common unit for area is meter square. So meter square is created by length times length, right? So meter square is, for example, if you have a square like this, the the area of this square, the area A, is this length times this length times this length. So it means that the secondary dimension is L squared. Okay, area is L1 times L2. So the unit will be in meter square. So this is the secondary dimension of area. All right? And then you have velocity and density. Let's derive this. Okay. So if we have so if we when we talk about velocity, the most common unit of velocity is meter per second. So velocity V, the unit is meter per second in SI unit, SI system. So meter is length over second is time to the power of minus 1. So this is the secondary dimension that represents velocity. And then one more example is density. Density, Pro. The unit is kilogram per meter cube. So kilogram is mass, meter cube is length times length uh, cube. So this is L minus negative minus 3, and this is uh, secondary dimension for the, density that represents density. Okay, so this is what we call dimension. We have a different system uh, of units that is commonly used in engineering, and the purpose of this is to remove ambiguity. This relates back to what happens to NASA when they lost their 125 million Mars probe. Okay, basically what happened is these two different teams, they were designing this probe together, and they one team thought they were using SI unit, and the other team thought they were using the English unit. So although they were talking about the same dimension, but they used different unit system, which caused a huge error, and then it caused the this accident to happen. So we have the international system, or SI. This is the system that we are most used to. It is meter, kilogram, second, and Kelvin for temperature. So uh, LMT theta. So the unit that we use is L. We use meter, mass, kilogram, time, second, temperature. We use Kelvin, not degree Celsius. We use Kelvin. Okay. So this is the SI unit system. Into SI unit system. We use this for. All right. And then we have the British gravitational system use foot, slug, seconds, and pound, and English engineering system that uses pound force and pound mass. Okay, this is not common to us, so our focus will be on the international system or the SI unit system. Uh, this system is developed so that uh, scientific and engineering community throughout the world can unify the standard. So we have a standard, so we can do comparison. Without any standard, we cannot do a proper comparison. It's like comparing apples to oranges, right? They're not the same. You cannot compare two things that are not same. So we have this system. We adopt one system so we can compare different quantitative values. Um, so we are not going to talk about the historical uh, context of how these systems are developed. It's not really important to us, but we need to know that when we are doing any uh, calculation, we need to look at the units, and so we use the proper system. Okay, for example, if uh, you have gravitational acceleration, right? So gravitational acceleration international in the SI unit is 9.81 meter per second. But if you're using the British system, we have another value and another different unit, which I do not remember. So when you look at any problems, you have to make sure that you identify what kind of unit system that you use. And for our purpose, most of the system that we use is the SI unit. But in real life, especially when you are designing things, when you want to buy stuff, maybe from the internet or from any hardware store, they might use different system. They mix it up. Okay, so people in the industry knows what they use. For example, if you were to buy a piece of plywood, of course, this is not related to fluid mechanics, but if you were to buy a piece of plywood, you will buy it they will measure the size of the plywood, the one piece of plywood in feet. So they will tell you, oh, which one do you want? 8 times 6, 8 times 4. Okay. So it's in feet, 8 feet times 4 feet, for example, 8 times 6, for example, 8 feet times 6 feet, or 8 times 4. But in Malaysia, the thickness is measured in millimeters. So they have 8 millimeters, 10 millimeters, 12 millimeters. So they mix these two unit system together. This is very common in hardware stores in Malaysia. So when you talk about units, you need to understand there are different kinds of system that you can use, and sometimes people mix them up. Okay, especially when it's related to common hardware stores that do not adhere to any system because they don't care. They just want to sell stuff. You as an engineer need to take care of all these units so you don't get it wrong. The best example is the one that I gave you just now, where the thickness of the plywood board is usually measured in millimeters. This is in Malaysia, of course, but the size, the dimension of the board itself is usually measured in feet. Okay. Uh, go back to our slide. Okay, so uh, you see here our primary dimension is mass, the symbol is m, and then the SI unit is kilogram. Length L is in meter. Time capital T. The unit is second for SI, and then we have temperature uh, capital theta. The unit is Kelvin. We have and we have this other system, right? There's one concept that you need to understand, that is the dimensional homogeneity. All right. Uh, as I said, we know that you cannot mix apples and oranges, right? Uh, but in engineering, all equations must be dimensionally homogeneous. Okay, it means that in one equation the dimensions need to be the same. So when you write an equation, you will write one side equals to another side, right? So although this is common sense, but equals to mean that it needs to be equal. The left needs to be equal to the right. For example, 3 plus 2 must equal to 4 plus 1. So both sides must be equal, equals to 5. But not only the value needs to be equal, the dimension needs to be equal on both sides too. All right? The dimension needs to be equal on both sides. The unit does not need to be equal. For example, 1 kilogram is equal to 1000 gram. So the unit does not need to be equal because the left side and the right side of this equation is still correct. It's still equal. The 1 kilogram equals to 1000 grams. So the unit does not need to be the same. But the dimension needs to be the same. And this is what we call dimensional homogeneity, right? Where the left side of an equation needs to be the same, the dimension on one side needs to be the same to the dimension in the other side. So if so we usually in engineering equation we have many terms, not just one. Okay. For example, let's take the Bernoulli equation. Okay. So the Bernoulli equation is what is it? T1 plus half rho, sorry, rho v squared plus, sorry, okay, plus rho gh1 equals to rho gz1, usually to p2 plus half rho v2 squared plus rho gz2, for example. Okay, so if you look at the units or the dimension on this side, it needs to be equal to the right side. So, and even each term needs to have uh, the same dimension. Okay, let's look if I got this right. So the dimension of term number one, this is pressure. So the term for pressure, the unit is Pascal, but this is also the unit is also Newton over meter square, which is also kilogram F equals to ma. So it's mass times acceleration. Acceleration is meter per second square over meter square. So basically, this dimension of the dimension for pressure is mass times mass over length, mass length, and time. Okay, so this is the dimension of pressure. Okay, this is the first term. Let's take a look at this term, the second one. This term. I might get this right, I might get this wrong. So this is half rho v1 squared. So rho is, unit of rho is kilogram per meter cube, and this is velocity meter per second squared. So you get kilogram meter squared per meter cube second squared. So if we cancel this, you get kilogram, which is mass, over length minus 1 and times -2. So we get the same dimension. Okay, so the dimension of this term and this term is homogeneous, it's the same. All right, and then let's take a look at the third term, this term. Okay, mm, so this is rho G Z1. Z is length. Okay, so rho is kilogram per meter cube density. Gravity is acceleration, so meter per second squared. And Z is unit is meter. So length, Z is length, its unit is meter. So we cancel this. So we get kilogram per meter second squared. So this is mass times length power negative 1 and time power negative 2. All right. So the third term is also the same as the second term and the first term. So it means that these three terms on the right side is also the same. So each term in this equation, in this entire equation, have the same dimension. So it means that this equation is dimensionally homogeneous. So it has dimensional homogeneity. All right. So when you are doing any analysis and you find yourself in a position to add two quantities, such as this one, we have 1, 2, 3, 4, 5, 6, 3 on each side, uh, and you see that they have different dimensions or different units, it means that, okay, it means that you did something wrong at the earlier stages of your analysis. So you have to check your dimension. Okay. Uh, I need to add one point. I said just now, equations on the left and right side can have different units, and this is very obvious when we write it like this: 1 kilogram is equal to 1,000 grams. Okay, this is true. But when you add two units in one side equation, 1 kilogram plus 1 gram, okay, uh, well, this is not good practice. Okay, although it is not wrong, but you cannot have these two units on one side of the equation. So you have to convert this into 1,000 gram plus 1 gram. Okay, this is, and then this is okay. And then you'll get 1,001 grams. Okay, so the unit needs to be the same in one side so you can perform the calculation. Although this is, I don't think this is wrong, but this is definitely not wrong. Okay, because it is dimensionally the same, left and right. But when you get to different terms, you cannot use different units uh, on one side of the equation. Okay. So and when I'm talking about units, I mean the scale of the unit. So this is actually gram and this kilogram. So it's actually the same unit. You cannot, but you can also say 1 kilogram is how many pounds, for example. So it still applies. So you can have different units on the left and right side, but you cannot have the dimension to be different. So in this case, this is the dimension is still the same on the left and right side of the equation. Okay, so that is what it means to be dimensionally homogeneous, or when you have dimensional homogeneity. Okay, this is a very important rule. So if the units don't balance, the physics is broken. All right. And now I'd like to move on to the next topic, which is the method of analysis. Uh, so when we are analyzing any fluid mechanics problem, uh, we have a choice to make. Okay, how do we actually track what is happening? So in the world of physics, we have two primary frameworks, which are the system approach, the left side, and the control volume approach, the right side. So These are two different ways to look at fluid, basically, and not only fluid, but this applies to different subjects such as thermodynamics. So anything that is related to physics, you will have these two approaches, even in mechanics, engineering mechanics. Okay, uh, let's take a look at one example. Okay, so let's take a look at when if we in a different subject, dynamics. For example, this is particle dynamics. So in particle dynamics, we deal with motion of a particle, of one particle, or maybe two or three particles. So let's say this particle, this is projectile motion. So the particle moves from one point, from point one to point two, and this is trajectory. So basically, in particle dynamics, what you can do is you can apply. We take this as a system. This is our system. So we can apply the Newton's second law equation, F equals to ma, to this system, and you can find what happens at point 2 based on your application of Newton's second law. So this is what we call system approach. Okay, so you apply the Newton's second law, which is one of the fundamental laws of physics, to a system, and then you can basically find what happens. All right, and this is also the same for in thermodynamics. All right. So before that, let me define what is a system in case you do not know. So a system, or we call the system approach, or we call this closed system, is identified as a fixed identity where you have the same particles in one space. All right. So it has a fixed identifiable quantity of mass. So the mass do not change, and you have a boundary, a very clear boundary, but the boundary can move or deform, but we cannot have any mass flowing in and out of the boundary. So you usually use this in solid mechanics and also thermodynamics. For example, for example, let's take a look at an analysis of a cylinder and a piston and cylinder. So you take as this is simple illustration of piston cylinder. Usually, we will set this. We are interested in what is happening to the gas inside the cylinder, right? So the piston will move down and then will compress the gas, and we want to see what happens to the gas inside this cylinder. So this dotted line, this is our boundary, boundary, okay? And the gas particles inside this cylinder, okay, all the circles that I'm drawing, let's assume that these are gas molecules. If there's air, so these are air molecules. Okay, H2O plus O2 plus H2 and so on, carbon dioxide and so on. Okay, let's just represent all these molecules by these circles, small circles. So within this boundary, so this is a closed system. Within this boundary, this partic particles cannot move in or move out. There's no way for the particles to move in or move out. All right? There's no particles moving in or out from the boundary, out of the boundary. Okay? Although you can have energy coming in and out, you cannot have any particles moving in or out. It means that the mass the mass of inside this boundary stays the same. It has constant mass. Even when the cylinder is pushed down, So instead of this gas being compressed, it means, for example, if the cylinder is right here, the piston is right here, I mean. So this is how the boundary looks like. So it means that all these particles, this mass will be compressed in here, but they are still the same mass. So if the mass is 1 kilogram, for example, this is also still 1 kilogram. So the mass do not go in and out. I mean, the molecules do not go in and out from the boundary. Okay, so this is what we call a closed system. Okay, and when we apply, okay, so this is the same as the example that I showed you just now for a particle that is moving in for particle dynamics. So we set this as our, let's say we set this as our boundary. Okay, so the particle moves, but but it's still the same particle. Okay, maybe we set this as our boundary, it doesn't matter, it's the same. So it is still the same boundary, and within the boundary, it's mass, the same mass. It does not change. And when we apply any physical law, such as Newton's second law, we can get the trajectory or the motion of the particle. Okay, so this is one approach uh, of what's the word? Is one approach to analyze uh, a physics of a system of a particle or many particles. Okay, a physical problem. So what we'll get from this is we will find a physical law, some expression, a mathematical expression. So when we apply this, we apply Newton's second law, and what comes out of this is a mathematical expression that expresses the motion of this particle. Okay, so if we apply the laws of thermodynamics, law of the conservation of energy to this closed system, and then what you get is a set of mathematical expression that expresses the changes of energy that's coming in and out from this closed system. So that's what we get when you apply. The point is to apply a physical law to a system in order to get a mathematical expression that expresses how this system behaves, how the particles or one particle in the system behaves. So that is the purpose. That is the purpose of us going through this process. Okay, that's how. And then what we can do is we will use this mathematical expression to solve our problem. Okay, that's the process. So we will identify a system, and then we apply fundamental laws of physics, depending on what kind of physical law that we want to look at, and then we get a mathematical expression, or maybe several mathematical expressions that we can use to predict the behavior of the physical system that we like to understand about. Okay, so uh, this is the definition of a closed system. Now we have one more approach, that is the control volume approach. Okay, this is different from a closed system because in the control volume approach, which is open system, we have a fixed region in space that we choose for our analysis. And it means that the region that we choose do not change. But mass can flow in and out. Okay, so if we look again at this system, mass do not flow in and out of this closed system, of this boundary. Okay, so this is the closed system. And then now we have another approach that we call the control volume approach. So I'll just write CV, which stands for control volume approach. Okay. In the control volume approach, we will set one region, and this region is fixed. But what will happen is particles such as air particles, okay, will flow in and out of the fixed region. Okay, so this boundary here, this dotted line is what we call our control volume. It is volume. It should be three-dimensional. If it's 2D, we still call it control volume. Okay, for example, this is a control volume. And then the surface of this each surface of, is what we call a control surface. This is our control surface, or CS. Right, so we have control volume and control surface. And then we have a mass that can come in and out of the control volume from any of the surfaces. So this is mass coming in and mass going out. Okay, so this is another approach that we can use. Okay, why is this approach? Why can we just use the closed system approach? Okay, let's take a look at let's look at one example. Let's say we have this airplane that has this massive wing, right? Okay, for example. So air comes in. So when this airplane is moving in this direction, we have air coming in from one other direction, and we know that this wing, this airplane, the flight characteristics of this plane is very dependent on the shape of its wings. Okay, so we have airflow going like this over the wing, and it will generate lift and drag forces that will affect the characteristics of the flight. So you have this lift and drag forces. Okay, so let's say you are an engineer and you're interested in studying the shapes or the effect of the shape of this wing to its flight performance. So you are going to do a two-dimensional analysis of this wing shape. So you have this wing profile that looks like this. Okay, okay, this is a bit ugly. We'll erase this and draw this again. Okay, let's say this is the shape of the wing. All right. So now, what you want to find from this wing is the force that lifts the wing and the force, the resistance, the drag force from the wing. This is what you're interested in, right? Okay. So imagine you have this one air particle, just one air particle that moves over this wing. Okay, so it's moving from here. It hits the wing and it goes over the wing and it goes here and it goes far away. Okay, it's just one. So what you're interested in is these two parameters, right? You are not interested to what happens to this particle. You are only interested about this particle when it is at the vicinity of the wing, how it affects the wing, how it changes this value and this value. This is the only moment in this scenario that you are interested in this exact particle. You're not interested at this particle when it is right here, and you're not interested in this particle when it is right here, far away from the wing. You're only interested on this particle when it is right here, and not particularly on this particle, but to what kind of behavior it exerts, what kind of forces it exerts and pressure and so on that it exerts to the wing, so you can understand the characteristics of the wing. Okay, so imagine you have many different you have billions of particles, air particles, right? Billions of air particles. I'll just illustrate this by coloring putting this color. So this color, let's say this color in this region represents all the air particles in front of the wing. So this will moved here over the wing, and so like goes like this over the wing, and some of the particles will go below the wing. Okay. So again, and then after it moves, it'll be right here, right? Again, you're not interested in these air particles when it is right here, and you're also not interested in these air particles when they are right here. You're only interested to the air particles when it is within this box. Okay, when it's right here, because it directly affect these two key parameters that you want to look at. This one and this one. Okay, so this is the gist of the control volume approach, where you fix your control volume, which is this box. So this is control volume. And again, it is actually three-dimensional. We only draw it like this because we are doing a two-dimensional analysis. And this is the box surrounding it, the surfaces surrounding this box are the control surfaces. And mass, in this case air, can come in and out of the control volume. And we don't mind this air coming in, this mass coming in and out, because what we want to look at is what happens within the box only, right? So this is the gist of the control volume approach. So there are cases when you like to analyze a physical problem using the closed system, such as this one, when you have a behavior of gas inside of a piston and cylinder system, and we know that this does not go out. So for this particular system, we is the most suitable system that we can use is a closed system. But for a system like this, when you we like to look at the effects of flow to the characteristics of a wing, it is much more sensible to use the control volume approach. Now, imagine if you were to use the closed system approach, where you have to look at the particles moving uh, at the same set of particles. So it means that you have to look at millions and billions of particles when they go over the wing and then go out and go back here. And it's not relevant anymore. So we are going to analyze billions of particles, and eventually the particle will go out from the region that we are interested on, and it's not relevant. It's too much information for something that we do not want to know about. All right. So in this scenario, in this case, it is much more practical to use the control volume approach. So that is why we have these two different types of approach: the open system and the control volume approach, or the closed system approach. However, uh, when you uh, when you define a system that you want to use, either you are using a closed system or you're using the control volume approach, you will get a different type. You will get different types of mathematical expression for each of the basic law. So usually when you apply our basic law and the fundamental law of physics, for example, when we apply F equals to ma, I mean, we apply the energy equation to this system because we want to look at the change of energy of the gas in the system. What we will get, you will get one set of mathematical expression. And most of the basic laws that we have, okay, these basic laws that we have discussed, hold on, the fundamental laws, the conservation of mass, the conservation of momentum, linear momentum, the conservation of angular momentum, first law of thermodynamics, or the energy equation, and the second law of thermodynamics. Okay, when we apply these five laws to a system, to a problem, usually the mathematical expression, this law is they are these laws, they are applied to the closed system. Okay, so they are applied to the closed system. This the closed system. Okay, so F equals to ma is actually applied to this system. The Newton's second law is applied to this system. The energy equation is applied to this system. So you actually need to bridge between these two. So how can you apply these five fundamental laws that is usually applied to a closed system so that it is applicable to the control volume approach. Okay, so the conflict is laws of physics, the five laws that we talked about just now, are meant to be used on a for a system or where the mass is fixed. But in our case, we are using most of the time we are going to use the control volume approach, where the mass is not fixed, rather the control volume, the region is fixed. So the solution where we can link these two is what we call the Reynolds transport theorem. Okay, so the Reynolds transport theorem will convert the system derivatives or the equation, the mathematical expression that we get from the closed system to the control volume integrals. So we will change it from the system approach to mathematical expression that is suitable to be used using the control volume approach. Okay, so this is what we call Reynolds transport theorem. And we will discuss this later. Will not discuss it now. So this is just an introduction of these two different approaches and why usually in fluid mechanics we will choose the control volume approach. Okay, so this is the same example that I use when you're analyzing a piston in a cylinder in an engine, for example. The gas expands and there's expansion and compression of the gas, and although the boundary moves, still have the exact same mass. The mass doesn't change, and it's permanently trapped inside the cylinder between the cylinder and the piston. So this is a closed system. And then we have another type of analysis like this pipe junction. When you are interested in the flow at this Y junction, okay, you do not care what happens to the flow after it goes out of this junction. You only want to know what happens in the junction. So in this case, it's more practical to use the control volume approach, where you look at what happens in this green box. So fluid can flow in and out from this green box, and we only care how it affects the area within this green box, and we do not care what happens to the fluid particles once it is out of the box and once before it comes into the box. So this is one case where we is preferable to use the control volume system. Okay, so I think these are the topics that I'd like to cover for today, and next time we will continue to chapter number 2, where we talk about uh, the more fundamental concepts such as velocity field, stress field, and so on. Okay, thank you very much.